What's good, Logan? All right, so we're going to be graphing some tangent and cotangent functions. So I've gone ahead and I wrote two functions, tangent and cotangent. They're almost the same except for the function. So they have the same exact stretch vertically with those fours. They also have the same exact horizontal stretch or shrink in this case because of the 5/3. So let's just get into graphing these guys here. So when I graph them, the first thing that I notice is that they both have four, or their vertical stretch by four. So that usually indicates that when I'm using my y-axis, what I'll do is I'll make sure that my y-axis is partitioned or drawn to the fourth line. The way I do that is I just draw a four. It's really simple. It's not that hard. I'm also going to do -4. I usually do this with most of the functions. So with sine, cosine, tangent, secant, cosecant, I'm always going to start with that vertical stretch. Next, anytime I'm dealing with trigonometric functions, I'm always going to break up my x-axis into four pieces. So I'll break it up into those four pieces right there. You know what? Looks like I could have gone a little bit more. So I'm going to go ahead and break it up a little bit farther just for visual purposes to help us see how this function is behaving over time. Next, I want to figure out how far each of those are. Traditionally speaking, it would be pi over 2, pi, 3 pi over 2, and then 2 pi. That is so that I can see the full wave, or I can see a full unit circle or circle rotation of 360 degrees, or 2 pi, however you want to think of that. Now, because of our horizontal shrink, right? So because of this value here, the 5/3, all of these values are going to change. They are not going to stay like that. So that's my next step. My next step is to go ahead and shrink those values by a factor of 3/5. So I take the 5/3 and essentially take its reciprocal. So I'm just going to write down what's happening here. So there is a pi over 2, and that is going to get multiplied by the reciprocal of 3/5. So I'm going to take the reciprocal of the 5/3, right? So I'm going to take the reciprocal of that thing, and I'm going to multiply it to all of my quadrantal angles. So I'm going to write that by 3/5. When I multiply that, that gives us 3 pi over 10. So I have 3 pi over 10, and that's what's going to get placed at that point value, 3 pi over 10. I'm going to do the same thing for the next one for pi. So I'm going to multiply the pi by 3/5. And we'll continue to do this for all the quadrantal angles. 3 pi over 2, we'll do the same exact thing. And for 2 pi, we'll also do the same exact thing. So all of them are going to get multiplied by 3/5 because the graph is being horizontally shrinked by a factor of 3/5. Now, when we're dealing with the tangent function, you could also at this time identify the period. We know that the period of a tangent function is traditionally pi. However, since we're going to be stretching it by a factor, shrinking it, sorry, by a factor of 3/5, why not multiply that by 3/5 right now? And we are going to see that our period is 3 pi over 5. So we can establish the period is 3 pi over 5. All right, let's go ahead and write down the rest of those quadrantal angles. So we have 3 pi over 5 at the originally 90 or 180, sorry, the pi angle. Then we have 9 pi over 10, followed by 6 pi over 5. Or you could say 12 pi over 10. So it's 3 pi over 10, it's 6 pi over 10, 9 pi over 10, and 12 pi over 10. They just happen to simplify. All right, so now that I got those quadrantal angles taken care of, let's get rid of all the math that went on over there. We can now start graphing it. Now, what we want to remember is that, actually, before I graph it, since it's going to be the same exact x-axis, y-axis for both the tangent and the cotangent, also for secant, cosecant, and cosine and sine, why not just copy, right? Let's copy that and let's just repeat, right? So rinse, repeat, but rather than rinse, I'm just going to move this guy right there, give myself some space so people don't think that they're continued with each other. So these are two different graphs. Now, the reason why I put these two functions next to each other is so you can see how the x-intercepts and the asymptotes are related to each other. Now, when you're dealing with a tangent function, what you want to remember, or at least what I want to remember, is that sine over cosine is how we define it. And I probably should have said x rather than theta, but what I'm thinking is that cosine defines all of my asymptotes because it's in the denominator for tangent, and sine is going to define all my x-intercepts. Now, since sine starts at 0 when we graph it, to show you what I mean, sine starts at 0 when we graph it, it would have looked like that, then I know that my x-intercepts are at all those zeros right there. So I'm going to put a 0 right there, I'm going to put a 0 right there, and I'm going to put a 0 right there. So for me, what I like to remember is that tangent starts with an x-intercept, right? Tangent starts with an x-intercept. However, cotangent, so because cotangent is considered cosine theta over sine theta, and sine theta is going to have 0, right? So sine theta normally starts here. That's what sine theta normally looks like. That has a 0 in the denominator, and that's where we're going to have all of our asymptotes defined. So while tangent starts with x-intercepts, I always remember that cotangent starts with asymptotes. So my asymptotes are how my cotangent function is going to start, and x-intercepts is how my tangent function will start. Well, what does that mean? Well, I'm going to have an asymptote right here, and then it's going to alternate between my quadrantal angles from asymptotes to x-intercepts to asymptotes to x-intercepts for both the tangent and the cotangent function. So if I wanted to go back, I can put x-intercepts on the cotangent function, and then I could put asymptotes on my tangent function. And notice the difference between the tangent and the cotangent function is they both have their asymptotes and x-intercepts swapped in their quadrantal positions. And that's because of what their denominators are in their respective sine and cosine functions. All right, so now that I have this, the next thing I want to do is I want to graph the halfway point. It's just a really special point that is taken from the idea that the tangent of pi over 4, traditionally, tangent of pi over 4 is equal to 1. And this happens between between 0 degrees and 90 degrees, right? Pi over 4 is 45 degrees. So it happens between 0 and pi over 2. So it's going to happen at this area right here. So I want to define that. Now, traditionally, that was pi over 4. But remember, we have a horizontal shrink by a factor of 3/5. So we're going to multiply this by 3/5 to find out what that actual value is. And it comes out to 3 pi over 12. 3 pi over 20, my mistake, 3 pi over 20. So now I know that my halfway point is going to happen at 3 pi over 20, and that's going to be true about my cotangent function as well, 3 pi over 20. Now, normally they go up to 1, but because of the vertical stretch by a factor of 4, they're going to go up. They're going to go up to 4. So I know that my halfway point is going to be located right there, 3 pi over 20 at 4, and 3 pi over 20 at 4 on the second function. Now, if you take a look at the unit circle, the pi over 4, its other angle that references 3 pi over 4, pi over 4 is 3 pi over 4, and then 5 pi over 4, and again at 7 pi over 4. Those are places located between every asymptote and its x-intercept. So in the middle, in the halfway between the asymptote and the x-intercept, right? The asymptote and the x-intercept, you're always going to have your halfway points. Now, I don't need you guys to identify all of them, but I would like you to identify that first one, the 3 pi over 20 in this case for both of these. All right, so now I have my halfway point. So if I wanted to write that down, let me erase the math, the work that's going on over there. So erase that. And then we'll write the halfway point. Okay, super technical term right there, halfway point. The halfway point is going to be located at 3 pi over 20, comma, 4. Now, that's not the only halfway point, but that is our first one. We can also identify our x-intercepts. So if we wanted to, we could say that our x-intercepts are at 0, at 3 pi over 5, and 6 pi over 5. So all I'm doing right now is reading my tangent graph. And then we can also identify our asymptotes. Our asymptotes are located at 3 pi over 10 and at 9 pi over 10. Okay. Now, if we wanted to do the same thing for cotangent, we could. If I wasn't using a digital notepad right here, I would probably have to rewrite all of this. But I'm just going to copy it, paste it, and then I'm going to redo some of the math, redo some of the words right there. So we'll take this one here, paste it. There we go. And this time, these guys for the cotangent function are not x-intercepts, and the asymptotes are not asymptotes. They swap. So now we're going to say that these guys are the asymptotes for the cotangent function, asymptotes, and these guys are the x-intercepts for the cotangent function. So you'll notice your x-intercepts and your asymptotes just swap between tangent and cotangent. However, your halfway point is exactly the same. Nothing changes by that. So we go ahead and graph our other points now. So we're going to, between every single asymptote and between every single x-intercept, we're going to have a halfway point, and they're going to alternate between at the highest and at the lowest. So between 4 and -4. So our next one's going to be at -4 because our last one's at positive, and then we're going to have another one at +4, and then we're going to have another one at -4. We'll do the same thing on the cotangent function. We start it up, then we're going to go down, and then we're going to go back up, and then we're going to go back down. And now we have enough points to actually get a really good representation of our graph if you know the structure of the function. So we make it look hyperbolic. So what that means is we're going to have like an S curve to it, some people would say. Oh, that kind of looked ugly right there. Sorry about that. So I graph it like that. So I would say it kind of looks like half of a parabola upside down and half of a parabola right side up, however you want to visualize that. So I try to make it look parabolic when I can, just following through with the asymptotes. So look, it's parabolic. It's I believe it's hyperbolic. I'll have to double check on that. But we'll kind of graph it at that curvature to it. And there you go. We have both the tangent and the cotangent functions. If you have any questions, please hit me up by email, or you can talk to me after class or even in class if you wanted to. All right, I'll check you guys later. Peace.